you guys able to hear me?
No, very faintly.
Okay. How about now?
Yeah,
Is that any
better.
Okay.
Can you share your screen?
Yeah, I just have to find out how to do that. There we go.
Great.
All right, are you able to see that full screen?
Yes.
Okay, perfect. All right, hi everyone, I'm Adam, and I'll be talking about some of our research investigating the effects of network topology class on firing behavior of spiking neural networks. So this is, these are kind of the very preliminary findings of a larger ongoing project into using spiking networks for associative memory tasks. So throughout this presentation, that's kind of the perspective I'm looking at things from. So, okay, so a quick overview. First, I'll go into some background on spiking networks and dynamic memory, and then I'll cover what exactly I mean by stable and unstable patterns, which is something I'll be talking about a lot. They're an important concept for dynamic memory. Then I'll talk about my experimental method. So starting with the model for the spiking neuron that was used, a brief overview of the network generation algorithms, and then I'll lay out the experiments that were done. So the experiments were done in two parts. The first was for neural networks containing 50 neurons, and then afterwards we looked into networks of 100 neurons. So here we refer to that as experiment A and B, respectively. So when I talk about the results in discussion, first I'll talk about the smaller networks, and then afterwards I'll talk about the larger networks. And the reason for this is just that some of the observations from the smaller networks guided our observations, our analysis of the larger networks. After that, I'll summarize everything and we can hopefully have some time for questions or comments. Okay, so for those who are unfamiliar, spiking neural network is different from a traditional or rate-coded network in that they incorporate an element of time into the computation. So what this means is that a spiking neuron, when it fires, its output signal doesn't travel instantaneously to subsequent neurons. Rather, every synapse in the network has a delay length property that specifies how long it takes a signal to traverse that synapse. And one thing that this can give rise to is if you might have a signal travel from one neuron to the next, and when it arrives there, it could trigger another, that neuron to fire, and then the subsequent signal could travel to a third neuron and so on. And if there's any recurrence in the network, then this can give rise to what's called dynamic memory, which is very interesting because it allows a network to have state without any actual structural changes to the network itself. And I'll talk more about that in just a moment. But one important prerequisite to have dynamic memory is you need to have a network capable of generating stable patterns, stable firing patterns, that is. And again, in just a moment, I'll talk in a little more detail about what I mean by that. So the two network topologies we looked at were Erdos-Renyi random graph networks and small world networks. The ER graph networks are, they're pretty commonly used with spiking networks. Some of the related works use them, so they're well known. And we chose small world networks because small world structures are very prevalent in nature, especially in biological brains ranging from roundworms up to humans. So the hypothesis being that maybe there's some useful properties there that we can find. Okay, so what exactly do I mean by dynamic memory? As an analogy, think of it kind of similar to short-term memory. Like I say, It's a memory that exists without changing the structure of the network itself. And what it looks like basically is you've got these signals running around in some recurrences of various complexity, and they cause one or more neurons to fire repeatedly in a regular pattern. And then if we can recognize that pattern, then that's something that we can use, and that's what we refer to as dynamic memory. So you can have a single network, and you can give it one input stimulus, and the network could generate, or it could converge to one stable firing pattern, and we could say that that's one memory. You could take the same network and provide it a different initial pattern stimulus, and it could converge to a completely different firing pattern. And the size, the capacity for these networks is very large. Regression analysis by Francis Jensen, based on some empirical experiments he did, estimates that the upper bound of the number of these patterns that could be exhibited by a single 25 neuron network is approximately 10 to the 12. So very, very much something that is of interest when you're looking at associative memory, things to use for associative memory. Another thing that Francis Jensen has is introduces a delay mapping procedure, which is a deterministic algorithm for constructing a decoding network that lets you take these dynamic memories and decode them into fixed time representations. So between that and the capacity, this is a very interesting area for if you're looking into associative memory problems. Okay, so what exactly do I mean by stable patterns? Well, when you give a stimulus to a spiking network, there's three possible scenarios. The first is that all neurons will end up in a regular repeating firing regime. And this is what we refer to as a stable pattern. The other possibilities are that there's not enough activity to sustain further activity, in which case all the activity will die out over time. We refer to that as a dissipative pattern. And finally, the network might not converge to a stable pattern. So those latter two cases we refer to as unstable patterns. And these are important because you can't really use unstable patterns for memory all that well. Okay, so and here's a visual representation of what that looks like. So on the right here, sorry, on the left here, we have a stable pattern, and as you go from the right to the left, you can see that every neuron is repeating its own pattern over and over again. Whereas on the right, if you start from the right, you see some initial inputs, and then as you move to the left, you see a little bit of sparse activity, and then it dies out. So that's a dissipative pattern. Okay, so now I'm going to talk about the method a bit. So I'll start with the neuron model. So this is a very simplified version of a leaky integrate and fire neuron. I won't get into all the math, but the important things to know for this presentation are that time is split up into discrete time steps. Neurons are binary. At every time step, they're either firing or not, so a 1 or a 0. Every synapse has a weight that is either 1 if it's excitatory or -1 if it's inhibitory. If a neuron receives at least as many, if the weighted sum of the incoming signals at any given time step for a neuron equals or exceeds its threshold value, which is 2 for every neuron in this paper, then the neuron will fire. For 2 time steps, and then it won't fire no matter what for 10 time steps. So very simple model. For network generation, the Erdos-Renier networks, they're pretty simple to generate. You have a single parameter PER, which is just the independent probability of generating a synapse from one neuron to another. We don't deal with self loops in this paper, so neuron A won't have a loop to itself, for example. The small world topology, it's a little more complicated. We use the Watt-Strigatz algorithm, where you start with a regular ring network, and then you perturb, you have a chance of perturbing each of the links. So this results in two parameters. You have K, which is the number of outgoing synapses you have from every neuron in the initial ring network. And then you have PWS, which is the probability for a synapse to be rewired. Okay, so experiment A, these are the experiments where networks all had 50 neurons in them. So what we did is we took, for the ER networks, we enumerated all the values of PER from 0.01 to 1 at intervals of 0.01. And small world networks, we did the same thing, except with K 1 to 50 and PWS 0.1 to 1. And so for each parameter or pair of parameters, we constructed 100 random networks and gave them 6 random input signals. And then we let them run for 3,000 time steps, so they had time to converge, and we recorded whether the resulting activity was a stable pattern or not. Experiment B is the exact same thing, except we used networks with 100 neurons, and our K value goes up to 100. So here's the results for the ER network with 50 neurons. So the vertical axis of the graph there is just how many of the 100 networks converge to a stable pattern. And you can see that there's a critical threshold around 0.04 for PER there, where the network goes from, excuse me, becomes stable for the most part. And this is consistent with the observations of Jensen when he did similar work. Here is the results for a small world network. Interestingly, we still have critical threshold. Here it occurs from K is around 18 to around 24 for lower to higher values of PWS. Nothing too exciting though. So I'm just going to go off topic for a moment here and talk about the computational complexity of running spiking neural networks, at least the ones using this particular neuron model. The complexity is directly proportional to the number of synapses in the network. And we can expect the number of synapses to be equal to the average number of the average in degree of each neuron times the number of neurons. So what we have on the right here is a graph showing the average in degree, the average of the average in degree taken over each of the generated networks for the small world networks. I don't have a picture for the equivalent picture for the ER networks because it's just a diagonal line. But since we know that the number of synapses is proportional to the in degree of the network, and we know that the performance is proportional to the number of synapses, we can divide the stability by the average in degree to get a rough estimate of the efficiency of that network in terms of producing stable patterns with respect to the computational cost. And the really interesting thing here is for the small world network, we see that this ratio hits a value of around 6, whereas it only gets to around 5 for the ER networks. So there's two major caveats for this though. The first is that when you have high stability, that's good. but stability is not necessarily sufficient for a variety of dynamic memories. There might not be enough variety in the number of patterns that get produced to be useful in practice. So that's something that would need to be looked into further. The other thing is that we don't know the rate of growth for this, for the difference between the small world network and the ER network for larger networks. It could be that this difference is insignificant and is only showing up because we're looking at small networks. Which leads to the next part, the second set of experiments, where we had 100 networks, 100 neurons per network. Again, here's the ER network's results. Nothing too unexpected. We have our critical threshold around 0.2 here, which is completely in line with the smaller networks, since the average integrity for 0.2 PER for 100 neurons is the same for the average integrity of 50 neuron network with PER of 0.4. And our small world network is also pretty much in line with what we would expect. The interesting things, there's two. The first is if we compare the ER results for the 50 neuron networks and 100 neuron networks, and we look at the region just around that critical threshold, we can see that the slope is actually higher in the larger network. And our hypothesis is that as the size of the network increases, the slope of that region around the critical threshold will also increase to a point. And the implication here is that as long as you have a sufficiently large network and you choose an appropriate PER value, you can just about guarantee that for the vast majority of input patterns that you will get a stable firing regime for the network. And that's a very useful thing to be able to know for a when you're dealing with associative networks. The other thing to note is we looked at the ratio from before for the larger networks of stability versus computational complexity. And we note that we're still seeing some difference here. So here we have about 4.5, 4.6 compared to about 3.5 or 3.6. So at least in this limited case, we still are seeing that difference. So overall, what we've done is we've made a comprehensive map of the effects on stability of the resultant networks of two topology classes for a wide variety of the parameters. As in previous works, we've found a critical threshold where results change from being unstable to stable. We found that the transition region around that critical threshold is smaller for larger networks, which could have useful implications for associative memory tasks when we need to guarantee stability. Future work here would be to continue testing for larger networks to see if our hypothesis holds. Does the slope continue to increase? We used a simple ratio to compare stability to a rough computational cost for the network parameters, and we found that for both 50 and 100 neuron networks, we have a higher value for this ratio for the small world networks than the Erdos-Regnier networks, which would suggest that the small world networks may be more efficient at generating stable patterns. And again, more work would need to be done to confirm this. Larger networks would have to be tested to see what the rate of growth for that difference is, if any, if it even remains significant. And we would need to actually look at the variety of patterns generated at those supposedly optimal spots to try and figure out if they're actually as useful as we would hope they would be. And that's all I've got to say. So thanks for listening.
Thank you, Adam. And let me start with questions and comments, if you do not mind.
Go ahead.
Oh, first of all, I would not say that dynamic memory is only property of spiking networks. As you,
Oh, no, sorry.
know very well, Hopfield network has attractors that are also a kind of dynamic memory, I would say.
Yeah.
And this is a related question. Would you call those dynamic memories attractors? You say that, well, I can tell you, I did similar simulations myself, and my supervisor, George Rascoli, did independently of me. And so I read some literature on this topic in the past. So I remember there are three kinds of behavior of activity in such a spiking network. It can be a stationary pattern, or it can be a randomly changing pattern, or it can converge to, well, actually there is a possibility of dying out of this excitation. There is a possibility of conversion into something trivial, or like point attractor, or there is a like pattern like yours, or there is a random randomly changing pattern. There is also the term runaway interference in such networks. But I am wondering if those patterns that you are mostly interested in are really stable or just stationary, because stability probably implies attractor properties, which means that if you introduce a small perturbation in terms of extra spike, the pattern would return to its original configuration. And also another question is about the dynamic laws. Do you consider plasticity in this network? Is it present in any form, or maybe there is a short-term plasticity, like short-term potentiation or short-term depression? That would definitely change the outcome. So, and I'm really surprised if you say that those patterns are stable in the sense that they can sustain perturbations, that there would be 10 to the 12 of such patterns. That seems impossible to me. Usually there are just few of those patterns in a network of that size.
Yeah, so I guess there's a few things there. First, I didn't mean to imply that that the spiking networks were unique with regards to dynamic memory. Sorry if I came across that way. So for this work, we haven't been accounting for noise in any way, and that's certainly a flaw with it. Francis has done a very large amount of work looking into the impacts of noise on this, and it certainly has a large impact. So yeah, the 10 to the 12 is less. It's not very realistic in terms of actual networks with noise. I don't have it here, sorry. I would have pulled out his regression diagram he had. So if we go back and we look at what I'm referring to as a stable pattern here, I suppose I might not be using it in the formal definition. And actually, if you had any recommendations for where I could go to read more about this, I would.
Yeah, there were authors like Maas, I believe, one of them. Okay, so.
Okay. So
and
this
you cited the book of Strogatz, so you can look into the definition of attractor and.
Oh yeah. So I haven't actually looked into whether or not they're attractor states or not. I think the confusion is my fault for using the stable pattern here in a kind of an informal way.
Because stability in mathematics or physics means something definite, not
Okay.
just a metaphor.
That's that's good to know. I was not aware of that, so thanks.
You are shy.
Sorry, what were the other parts of the question?
Yeah, so basically you answered. The other part was how about plasticity, long-term or short-term plasticity?
I haven't looked into the effects of plasticity yet. That's actually next on my list of things I need to try. I've been recently in my work, I've been trying to actually use these patterns. I've been trying to use them in a similar use case to an autoencoder, so very similar to a Hopfield network.
Okay, then maybe the last question is what is the practical use or scientific finding here? Like, would it be a model of realistic brain networks, or would it be useful for AI, or what is the potential?
So this would be a very preliminary work. Basically, so I guess the idea is you can have these patterns here that are repeating regular patterns, and you can get a very large quantity of those corresponding to your input. So you give it one input, you'll get one pattern. You give it another input, it'll give you another pattern. And there can be some amount of, so before it converges to the pattern, there can be some amount of attraction between the states. And a hypothesis that I've kind of been working on is that maybe we can use this as a way to bring similar input, to try and link our input patterns, our input phenomena into these repeating states that we could then decode and use it similar to a Hopfield network. So for example, if we have, if we're using like the MNIST data set and we have a letter, a character, a picture of a character, and we feed the pixels in as input, and then we feed it a slightly corrupted version of that letter, can we get those two patterns to, those two input patterns to converge to the same spiking pattern? And the reason why we're looking at this in terms of spiking networks instead of Hopfield networks is because of the sheer number of these patterns that you can store in a spiking network. So the idea is that we may be able to find a higher capacity way of doing autoencoding with this, but it hasn't been all that fruitful so far.
So these are exactly the questions that I wanted to ask. They remain, as I understand, the capacity and the reliability, the stability of those patterns. Because what you admitted yourself, 10 to the 12th, is not a realistic number.
Yeah.
And then what is the truth? Maybe you have only 3 or 5 such patterns, right? Or what is their stability with respect to noise and perturbations? Even if you build those networks from logical circuits based on transistors, still there is a possibility of an error. Yeah. So, okay, I guess Nate has questions now.
Yeah, it's actually related to the questions you're asking. So related to Dr. Samsonovich's question about what is the biological connection potentially or purpose. It's interesting that you looked at the computational cost compared to capacity, but there's like when a certain subject area, when I'm researching the hippocampus is the dentite gyrus is theorized to create pattern separation by using extra neurons to store patterns instead of like the least number of neurons it can use. So there's kind of a confusion cost as well. So because having very similar types of patterns can be biologically confusing for an organism to try to recall the correct pattern. So I think, have you thought at all potentially about also exploring in the future looking at the probability of memory confusion as a potential factor, as well as the capacity for storing patterns.
Yeah, I think that's going to go hand in hand with the with noise. I mean, different cause, but it's going to have the same effect. It can result in the wrong memory coming forward, and for sure that's something that could be looked into. In terms of what I've been trying to do with this is, so right now to try and construct these networks that can hold these auto-associated memories, I've been using an evolutionary approach. And for a fitness function, I've been looking at using Fisher's discriminant. And so what that's able to do is it can, it will give you a high value if two patterns, if two distributions are far apart, and a low value if they're close together. And it'll also give you a higher value if you have tighter spread than wider spread. So I'm trying to look into computing a Fisher's discriminant value for these spike plots to try and say, okay, how similar is the spike plot to another spike plot from a related phenomena, and how similar is it to a spike plot from an unrelated phenomena? Because obviously we want to keep those far apart and we want to keep those close together. Unfortunately, I've been not having any luck in getting the discriminant to work for me, since there doesn't seem to be enough correlation in what I've done so far. So.
Well, thank you. It was a great talk. Thank you.
Oh, thanks.
Okay, are there any other questions? No? Then thank you, Adam, for your talk.
Thanks for listening.
And we shall proceed with our last talk for today, and I believe the last oral talk for BICA 2021 by Alex Secho.